Hello everyone, welcome to MESS e-learning channel. So we'll be solving another problem based on equilibrium in connecting bodies. So this is the problem here. So we have a question this side here. So if we see, we have two cylinders, one being the A is 1000 Newton. So A is 1000 Newton and the weight of B is 750 Newton, as they have written the weight of cylinder A and cylinder B is 1000 and 750 respectively. And in the last we have been also provided with the radiuses of the following balls. So for A, the radius for A is 400 mm and for B it is 300 mm, and we have to find that the reaction at points 1, 2, 3 and 4 also. So, and the most important information is that the system is in equilibrium. So as the system is in equilibrium, we need to separate this from the given environment and we need to draw a free body diagram. So I'll draw a free body diagram first. So let's say this is cylinder A and this is cylinder B, this is B and this is A. So at A, if we see, we have a point which is in contact with the wall at an angle of 60 degree. So there will be a reaction force at point 4 which will be here. So reaction at point 4, we'll call this as R4. Also, that is the normal reaction from the wall at point 4. Also we have the cylinder A and cylinder B in contact at point 3. So ball B will be providing a reaction or giving a reaction to A, and the A will be giving that same reaction back to B. So also there would be a reaction from the ball B which will be R3 because the point is given as 3. Then there will be a self weight which will be acting directly downwards. That is, for B it is 300 mm. Sorry, the weight is 750 newtons and the radius is 300 mm for B. Now here we have cylinder B. So here directly we can see that we have a support reaction from the base that at point 2, that would be R2, and the the reaction from the wall at point A, which will be here, and that is R1, will also be having the reaction R3 back from A to B. So we'll have that reaction R3 here, and same will have a self weight of 1000 Newton. It is given. So now there is one thing that we need to find here is the angles that the forces are acting. So if we consider this R4, if I draw this will be 90 and this is given as 60. So if this is 60, this would become as 30, which is why this would be 30 degree. So here with X, I'll have this to be, the R4 with X will be 30 degrees. Now we need to find the angle R3 also. So that is the in-between force. So if we have anytime we have this kind of a question, one solution can be, we connect the two cylinders center to center and we drop a perpendicular and I join them. I need to find this angle theta. So if we have any of the two sides, I can directly calculate theta. So let's see if we can find that. So here this distance is already known, because this distance till the point of intersection would be the radius of ball B, and this distance would be the radius of ball A. So let me draw the triangle here. So this is my theta, and this we have already found that it is the addition of both the radiuses. Till here the radius of B, and till here the radius of A, that is 400 plus 300, which would be 700 mm. Now this side, it is not possible to find this side as it is in between the cylinder somewhere. But then the remaining side that we can try to find is this one. So if we see this, now here I have the distance from this vertical wall till the point A. Till here I already have the total distance. So if I find this distance, I can subtract it from 700 and get the distance. So here we already know this distance, because it is exactly same as that of the radius of B. So this would be how much? 300, and the distance from this point to this point is 700, which is already given. So this would become 400 from this point to this point. So this is 400. Now we can find the theta. So for theta, if I need to find, it can be, so this is adjacent to theta and this is the hypotenuse. So it can be cos inverse of adjacent upon hypotenuse. So now that is cos theta is equal to 400 upon 700. So bringing cos back here, it would be cos inverse. So theta would be 55.15 degrees. So I have theta now, and theta would be here, which is 55.15. And next I have theta here also, that would be same, it is 55.15. Now we can solve this. Let us solve and find the support reactions at point 1, 2, 3 and 4. So to solve that, we need to select which cylinder we should solve first. So here if you see, in cylinder A we have only two unknowns, and for concurrent force system we have only two equations of equilibrium, that is f of x is equal to 0 and f of y is equal to 0. And here we have three unknowns, that is R1, R2 and R3. So we can solve this. So we should start with A. So if I solve for A, we have only three forces acting towards the center. So we can use Lamy's theorem here. So by Lamy's theorem, I'll first write this, that is 750 Newton will be proportional to the sine of angle between the other two forces. So this is, here I have the force and the other two forces is this. So the angle would be this one. So this angle would be 180 is the complete angle. So 180 minus 55.15 and 30 would be this angle. So this would be sine of 180 minus 55.15 minus 30. Here this angle is 180 minus 55.15 minus 30. So I have written that. Next would be, let me consider R3. So R3 will be this force and is proportional to the, for this R3 is proportional to the sine of angle between the other two forces, that is R4 and 750. So this would be sine of the angle between these two, these two forces. So this is 90 here. So it would be 90 plus 30. So that would be sine 90 plus 30, this angle. And now the last one would be R4 4 upon sine of angle between the other two forces. So this is R4, so the angle would be this complete angle here. So this angle, it would be, this is 90, so it would be 90 plus 55.15, and that would be sine 90 plus 55.15. So now as we have the equations, what we can do is, we'll compare these two first and we'll get the value of R3. Then we'll compare this one and this one to get the value of R4. So if I solve for R3, my equation would become 750 into sine of 90 plus 30. That is, I am equating these two. So this would go here, 90 plus 30 divided by sine of 180 minus 55.15 minus 30, which would become 869.14 Newton. That is R3. Now if I calculate for R4, for this one the equation would become this, and this we are equating now. So this sine 90 plus 55 would go up. So that is 750 into sine 90 plus 55.15 divided by sine 180 minus 55.15 minus 30, which would become, which will give me R4, that is 573.48 newtons. So now I have R3 and R4. Now we need to find R1 and R2. So we'll come to the cylinder B. So here we already know R3, so we can substitute that here. Now we have only two unknowns left, which is R1 and R2. So here, as we have four forces, we can't use Lamy's theorem. We'll have to be solving this cylinder by the traditional equilibrium equations, that is f of x is equal to 0 and f of y is equal to 0. So if I equate f of x is equal to 0, we only need to simplify, resolve this. So this would become R3 cos 55.15, and this would become R3 sine 55.15. So now for f of x is equal to 0, we'll equate all the forces in x direction to 0. So this is R1 in the positive direction minus R3 cos 55.15 equals to 0. So here I know the value of R3, so I'll write that as, so R3 here I have, that is 869.14 cos 55.15. So if I solve this, I would get R1 to be, R1 equals to 496.65 Newton. Now I have R1. Now I'll solve for f of y equals to 0. So for y, if we solve, we have R2 as unknown first. So R2 would be positive as it is going up, minus 1000, that is it is going down, and also minus R3 sine 55.15 equals 0. So I'll substitute R3 here. So I would get R2 equals to 1000 plus R3 is 869.14 and sine 55.15. So if I solve this, I would get R2 equals to 1463.26 newtons. So now I have the values for R3, R4, R1 and R2. So we have found all the contact reactions, the reactions here, that is 1, 2, 3 and 4. So this completes the solution. Hope you understood. Thank you.